What are the different types of quantum error correction? In order to understand the different types of quantum error correction, we first need to understand what quantum error correction is. In its simplest form, quantum error correction are tricks and techniques used to protect sensitive quantum information. Sensitive quantum information is basically saying that information coded into quantum computers is sensitive. But why is this? This is due to the fact that quantum computation uses qubits, which are the quantum computational equivalent of a computer science bit. Qubits are typically made of particles such as photons or ions. These particles are subatomic and therefore are sensitive to quantum phenomena. There are two quantum phenomena that make them sensitive. The first one is entanglement, and the second one is decoherence. Entanglement essentially correlates qubits, aka makes them act kind of like a single connected hive mind, which is wave-like behavior. This makes them sensitive and prone to errors because if there's an error in a change in one qubit, it spreads to all of them because they're all connected. And the next is decoherence, which makes them extremely susceptible and sensitive to even minor changes and disturbances due to their size. For example, temperature, electromagnetic waves, or any perturbations, which basically means disturbances. All of these would end up messing up the qubit state, which is the equivalent of messing up the ones and zeros in binary, which would lead to a lot of programming errors. So now we can finally get to the types of quantum error correction with this background. The types I'm going to discuss are the ones that quite frankly interest me the most, which include surface codes, cat codes, trapped ions, and concatenated codes. So let's start with the most common form of quantum error correction, which is surface codes. Surface codes, qubits are arranged on a 2D grid called a lattice, which kind of looks like a chessboard grid type thing. When put into the lattice, the qubits inside work together to fix errors without measuring each other, which is good because that would change the state. Again, changing the state of a qubit is the same as changing a 0 to a 1 in the code of a bit, so it messes up everything. This whole checking system inside the lattice is called the parity check. They work because in the lattice, the qubits all compare states and compare the states in the other lattices to their own. This checking basically happens because the lattice bonds them. The next form of quantum error correction we're talking about is cat codes, which is inspired by a Schrödinger's thought experiment with the cat that I'm sure you've heard of. It's related to this thought experiment because it involves qubits being put into superposition of two states, similarly to how the cat was in a superposition of life and death until you open the box. This superposition results in entanglement. This entanglement creates a cat state where entangled qubits protect each other from specific types of errors. By that, I mean it only protects against certain types, not all types of errors. The next method of quantum error correction is trapped ions, which are individually charged atoms. Ions are held in place by an electromagnetic field. This electromagnetic field is created with electrodes, which are conductive material that makes EM fields, which are the same thing as electromagnetic fields. This EM field basically traps and stabilizes the ions by keeping them balanced. Lasers are then used to manipulate the ions into different values in quantum operations to code the quantum computer. And finally, the last method of quantum error correction that we'll be talking about today is concatenated codes, which are basically more advanced versions of surface codes. They involve stacking layers of surface code lattices on top of each other, each layer catching a different level of error, allowing less error to go unnoticed. It's like a layered filter. And that concludes our topic for today. In front of you right now is a visual guide for those who like to have that on hand that I made. And just note that I am not a professional by any means in physics, so if you have anything to add, anything I got wrong, please comment below and I would love to learn from you and expand our knowledge together. I hope this video taught you something. Stay curious and keep questioning.